Now I have moved this 1 or 2 residues down, and here the backbone part of this is certainly in the hydrocarbon part, roughly here where my hand is, right? But you see what that lysine is doing? The lysine, due to its long neck, the side chain, is actually stretching out. So this side chain is certainly not whisking around and sampling the interior parts of the membrane down here. It's always sticking up to pair those hydrogen bonds. That's an interesting concept. Let's continue. Let's pull it even further down. So now I have actually introduced 2 of them. Do you see what happens here? Each of those lysines, they're almost in the middle of the membrane now, and yet they are not, because the actual charged part on the lysine side chain is located, by stretching this out, it's located reasonably far up. They have to pull in a bit of water, or do you see what it's interacting with? It's pulling down a lipid a bit. So it's taking the carbonyl groups of the lipid. And I think that's roughly what happens here too. So the positively charged side chain can interact with those partially negatively charged oxygens in the carbonyl. But that's going to create a force on the side chain. And if I now have 2 of these residues on opposing sides of the helix, do you see what the helix is doing? It's tilting. And this you can even see in experiments, that there is going to be a systematic tilt depending on where I place hydrophilic residues. Do you notice how I'm almost contradicting myself? Because I said that charged residues really couldn't go in membranes. And on one hand I'm right, because they are not really in membranes. But they are in membranes in the sense that among these 20 residues in the helix, I'm certainly having 2 residues that are arginines embedded relatively far into a helix. It's not going to be good to have it this way, but it is possible. We can continue this pattern. You can take many different hydrophobic or hydrophilic residues and just check what happens in a simulation. For some of them, if I had a full charge, that's so bad that I need to have water around it at any cost. But if I take something that's merely polar, I think, what is this? It's a methionine, I think. The methionine here is a bit polar. It's certainly not going to be happy here, but it's not so unhappy that we can afford the cost of taking water all the way in to solvate that side chain. So for methionine, apparently the methionine will rather make do and accept that it's not going to have a perfect hydrophilic environment. What happens if I introduce another residue? Say that I take that arginine. Do you see the difference here? The arginine is so charged that at any cost we can't afford to keep that charge in the membrane. I have to pull in water, even though this means destroying the membrane locally. You're not seeing the lipids here, but trust me, they are around. And this is an interesting concept. The reason why this happens is that taking a full charge and solvating it in oil, it's basically not going to happen. I'll hide myself for a second here, but this is a hydrocarbon environment. This would be pure oil, but this is also how the lipid environment will look to a charge. If I take this environment and try to put a sole charge in here, we can actually measure experimentally roughly how costly that would be. That would be roughly 20 kilocalories per mole. I'm not sure if you have any gut feeling for that energy, but this energy is eat my left shoe territory. There is no way on earth this will happen spontaneously. It's going to be once in a billion or so. Forget about it. The arginine residue would rather deprotonate itself and becoming neutral, paying a lot of energy for that than to introduce the charge in the middle of the membrane.